Okay, now let's talk about what happens. What if the region D is not simply connected? Okay, simply connected meant no holes. So what if there's a hole? So as an example, what if you had D is the space between x squared plus y squared equals 4 and x squared plus y squared equals 25. So if we were to draw a picture of that region, we would have, okay, so there's circle of radius 2, and then a circle of radius 5, and we're filling in the part in between, sort of like a flattened donut. Okay, and so that's the region D. Maybe we use a color so it might be more visible. That's D right there. So then the thing is, we can actually, let's make the following claim that the boundary of D has two parts. So the boundary means like right on the border. Okay. So what are the two parts? Well, if we were to draw those, it would look like this. So there's this circle of radius 2, and then there's the circle. Let's draw the 2 closer to the axis though. And then there's a circle of radius 5. Just off to the side, let me just note that like when you have a filled in circle, the boundary is just the one outside circle. So this is what I mean by boundary, right? It's like this the points along here outlined there in red are the boundary because each point in red here it touches a filled in point and an unfilled in point. So there's black points going this way and there's white points going that way. All right. So in this case, there's a boundary piece right there, and then there's a boundary piece right there. And what we're actually going to do is I'd like to name the inner circle boundary C sub 1 and the outer one C sub 2. It doesn't matter really which one you name which, but I just want to give these a name. And the outer circle, we're going to orient this. The appropriate orientation is counterclockwise. Oddly enough, the inner circle, the correct way to orient this is clockwise. So let's draw in a couple arrows to show the clockwise orientation of the inner circle. Now that might seem strange to you when we've been saying, oh, the usual way to orient things is counterclockwise. So how come that inner circle would be clockwise? So let's talk about this. So why this oddness of one circle? The outer circle is oriented counterclockwise and the inner circle is oriented clockwise. Well, let's just say that even though Green's theorem, and we haven't left out all the details of exactly all that, but like we only said that Green's theorem earlier applies to simply connected regions. So let's point out, let's do the following. Okay, let's say that Green's theorem applies to. Let me draw two pictures of regions that Green's theorem actually does apply to. Okay, so we're going to, they need to be simply connected regions. So regions with no holes, well, here's one of them. Doot, 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 that. Let me just do that. Okay, so this filled in region here has no holes. Okay, there's a little cavity in here, I get that. But there's no hole here, right? So, and then another region that I'd like to draw would be, okay, circle the bottom half of a circle of radius 2 and the bottom half of a circle of radius 5. And let's connect there and there. Sorry, the axes are getting in the way. Let's shade in this. So the two blue regions here are different, but each of them is a simply connected region and Green's theorem applies. Now, if we were to compute what is the boundary, of course, if we don't want to write the word, we could just draw the symbol for boundary. Again, the boundary, let's compute what the boundary is. Well, for the first shape here, the boundary, let's draw this in red, would be traveling counterclockwise through the entire shape would be that shape. Okay, that would be the boundary. For the second one, here, if we were to draw a picture of what the boundary would look like, well, again, we need to travel. So from inside the object, when you're right on the edge, we've got to travel counterclockwise. But we better continue traveling in that direction, the direction we were traveling, and keep going. We don't want to reverse, and then keep going. And so these would be examples of what counterclockwise movement for this filled in region here would be. Okay? And then the thing is, the integrals along these line segments what do I mean by these line segments? So I mean this one here and this one there. These cancel out. It's because you've got the arrows in opposite directions, right? So over here it's pointing to the right, over here it's pointing to the left. So these are arrows in opposite direction. Let's write that better. Arrows in opposite directions. So it doesn't matter what function you're integrating. It's just that you get the value once positive and once negative with the arrows pointing in opposite directions, and those integrals there would cancel each other out. And then same deal, right? The integrals along these line segments cancel out. So by the word these now I'm talking about that line segment here and then this line segment there, because these two line segments are the same line segment just pointing in opposite directions. So look, if having the integral along this and along this each contributes a number but they're opposites of each other, and then the integral along this and the integral along that each contributes a number but they're opposites of each other, let's just not include any of them, right? Let's include none of them, and then if we draw all of the curve that's any pieces of any of these curves that are in red but not circled, because this part cancels with that part, and same deal, this part cancels with that part, then what do we need to draw? We'll draw, let's draw this upper half there, and that's this part of the circle of radius 5, and then the lower part down here is this part of the circle of radius 5, and then all that's left from the first diagram here is this part here. We didn't really draw in an orientation arrow, should have done that, just we need to travel along here without backtracking, so that'd be this traveling clockwise for the circle of radius 2, and then the bottom half here we did already draw in these arrows, right there, and so we'll draw this in right there. And the point is, no need to draw in this part because it's once this way, once that way, and they would just cancel each other out. Same deal, no need to draw in this part because it's once to the right and once to the left, and those two integrals along that piece would cancel each other out. So I hope it's a little convincing here that the boundary, if we follow the orientations, the boundary with orientation would be the following. So the boundary of D is two things, right? It's a counterclockwise circle of radius 5 and a clockwise circle of radius 2. So let's actually now compute an example. And so let's question, let capital C be capital C1 union C2, where, well, C1 and C2 are actually what we had just seen earlier. We're just going to define them to be what we just saw a moment ago. C1 is the clockwise circle of radius 2 centered the origin, and C2 is the counterclockwise circle of radius 5 centered at the origin. Okay, with that definition in place, let's find the integral over c of x to the sine x power plus 3y dx plus quantity 10x plus root y to the fourth plus 1 dy. Okay, just as a comment, let's note that this, with the first part here, we had done. So the circle of radius 2 centered at the origin, in fact, even with the orientation being clockwise, this we did at the beginning of class. We already did the work, so we're going to borrow some of that work. Okay, so, all right, in starting the answer, let's just draw the following picture. That there's this circle this way, oriented clockwise. There's a circle this way of radius 5, oriented counterclockwise. The region in between is here. So that's the appropriate, we'll call that capital D. It is the appropriate region that would have boundary C1 together with C2 with the appropriate orientations. Okay, so what we're doing here is we're talking about, and you can look inside the book, but look at a thing called using Green's theorem with a hole. We've built up all the pieces to do it. I think it's helpful to do some additional reading. So here's what we're going to end up with, is that this integral here ends up being equal to the double integral over d of 10 minus 3. It's really dA. Same deal as before. The 10 here is partial derivative of q with respect to x. Okay, so take a look at this differentiate with respect to x. And then same deal as before, this after the minus sign is 3, and that's, if this is p over here, x to the sine x plus 3y, we had differentiated p with respect to y. It's just because that's what Green's theorem requested, dA. And the point is, instead of writing this as a dx dy integral or a dy dx integral, that's not what I want to do. Take a look at the shape. If we're integrating over d, it makes sense to do this in polar coordinates, right? There's no other format here that would make any different sense. In polar coordinates, integral, we'll just copy down the 10 minus 3 as a 7. The dA becomes r dr d theta. R dr d theta. And r this time goes from 2 to 5. Yeah, because we don't have the part in the middle. Theta goes from 0 to 2 pi. Now, if you work out this integral, somewhere along the way, I'll skip the details, but I'll just mention that if you work out the integral yourself, you're actually going to see at some point 175 pi minus 28 pi. And I will just comment that earlier we had seen the minus 28